This video is about combining inductors and capacitors. We're going to look at two different ways of doing it. We can look at an inductor and a capacitor in series, or an inductor and a capacitor in parallel. Let's look at the math for each of these. What's the impedance of each of these things? Well, if two things are in series, then the impedance is just the sum of the two impedances, so that's j omega L plus 1 over j omega C added together. And we can clean this up a little bit by putting it over a common denominator, just making the j omega C on the bottom. So we could also write this thing as, well, j squared omega squared LC. J squared is just minus 1. So I'll get 1 minus omega squared LC on the top and j omega C on the bottom. Over here, when we've got them in parallel, we're going to get z equals 1 over j omega L plus j omega C. And here we can clean things up by multiplying top and bottom by j omega L, and we'll get this is equal to j omega L divided by 1 minus omega squared LC. Now, you may notice that in both cases here we have a purely imaginary number, and because there's an imaginary divided by a real, or a real divided by an imaginary. And also we have a strange phenomenon where there's a number that goes to 0, either in the numerator or the denominator. And that going to 0, where omega is equal to this 1 over the square root of LC, that's the resonant frequency. Or if you want to be a little bit more careful about that, you could write F equals 1 over 2 pi square root LC. So we're talking about frequencies rather than angular frequencies. Okay. What else can we tell about the LC circuits? Well, we know that the resonant frequency, this one, 0 at resonance, and this one is infinity at the resonance. What about at low frequencies, as omega goes to 0? Well, as omega goes to 0 here, the top part goes, the omega squared basically disappears, and we get that this goes to 1 over j omega C as omega goes to 0. And we can also look at what happens as we go to infinity. Now the omega squared is the one that really matters, and the c's will cancel, one of the omegas will cancel, and we'll get, it'll go to j omega L as omega goes to infinity. And doing the same sort of things over here, as we go to 0, the bottom disappears, so this goes to j omega L as omega goes to 0. And as omega goes to infinity, we'll get, again, this part disappears, and we have simplification goes to 1 over j omega C as omega goes to infinity. All right. Notice that we ended up with just an inductor, or just a capacitor, or infinity. And here we ended up with just a capacitor, just an inductor, or 0. But where it's a capacitor and where it's an inductor are swapped with each other. So if we look at the series arrangement here, we're going to get that it behaves like a capacitor at very low frequencies. So it's going to come down straight line like that on a bode plot, and then it's going to be like an inductor at high frequencies, and in between here it's going to go to 0 at the resonance, so that it's suddenly going to go shooting way off down to minus infinity on the log-log plot. So that's what the series arrangement looks like. And the parallel one is going to do pretty much just the opposite. It's going to come up as an inductor, shoot off to infinity, and then come back down from infinity like a capacitor. Let's take a look at this thing in GNU plot. So I'm going to create a GNU plot script, which I load the definitions so that I have the definition of ZC and ZL, the formulas for the impedance of inductors and capacitors. I've got setting up the frequency range. Here I set a format so that I can see that the output is in ohms. I'm just going to plot the absolute value of the sum of the two impedances, that's the series connection, and also I'll take the parallel connection of two impedances and just plot that. Let's go to GNU plot terminal, load it, and let's bring up the result. We've got here for the series connection, it comes down like a capacitor, shoots off to 0 here, and then comes back up as an inductor. For the parallel connection, it comes up as an inductor, then shoots off to infinity at the resonance, and then comes back down as a capacitor. And notice that once you're a factor of about 3 away from the resonance, it behaves pretty much just like a simple inductor or a simple capacitor. Only one of the two components really matters once you're away from the resonance. But right at the resonant frequency, things get very interesting indeed. And LC circuits, when they're done deliberately, are done usually to take advantage of this sharp resonance. Sometimes you get LC circuits that are unintentional, the result of parasitic capacitances and parasitic inductances, and then you need to know where is this resonant frequency happening because you want to avoid it and rather than wanting to see it.